Okay, today we're going to be going over section 5C and 5D. These two sections are not going to take long. They're more about interpreting, so we're going to talk more, kind of focus on the interpreting, not at first, actually, it kind of leads to that, but interpreting graphs and things of that nature, which I think we've talked a little bit about before, but we'll go a little more in depth today than in previous sections. Okay, so let's get rocking and rolling. So I'm going to start the lecture. I'm really going to start in section 5C. It's on page 310 if you're following along in the book. First off, do you guys in the class have any questions about the first two sections, about 5A and 5B? It was really just a lot of definitions, right, from 5A and 5B. And I would kind of focus on the definitions, but that's the main part, especially at 5A with those foundations of statistics. So you can raise your hand, you can put a question in the chat. Either one is okay. Okay. So if I see one pop up, I'll answer it. No big deal. So let's start in 5C. 5C is about tables and graphs, and I'll tell you, this semester is a little different because you won't be able. We're only doing Blackboard tests, so it's a little different with this section, because in the past I would have typically make you make a frequency table or make a pie graph, but it'll be more about interpreting those for this class for today and for the test, how I'm going to test it. So if we look at 310, page 310, the first thing your book goes over is the frequency table. It's the most basic form of of data representation, right? It's where you just tally something up and then you put it in a table. The book does, and then you just give its relative frequency. The book gives an example. Well, I'll kind of talk about the example and how I would ask this on the test. So example 1 says, add to table 5.1, column showing, wait, where's table 5.1? Oh, okay. No, let's start before that. So the top of that page, it says frequency table. The teacher makes the following list of the grades she gave to her 25 students on an essay. And you can see they're all written out. It's like A, C, C, B, C, D, C, C, F, D, C, C. And she just gives every single test grade for those 25 students. And it's just hard to interpret that, just seeing them all listed out. And so what we can do is make a very, very basic frequency table, which is just 2 columns. And the first column is the type of grade. So they've got A through F, right? A, B, C, D, and F. And then the frequency is just the number of students that made that grade. So if you look at this on page 310, table 5.1, which is on the left, for an A, there were 4, B, there were 7, C, there were 9, and so on. So the relative and cumulative frequency, though, give the actual percent that made that. So, it doesn't tell us that. If I just told you, hey, you know what? There were 4 students that made an A on my first test. I mean, we don't know how many students. What if there were only 4 students in the class, right? That means 100% made an A. Or what if there were 100 students? That means only 4% made an A, right? So it doesn't tell us much by just saying, it doesn't paint the entire picture, I should say, by just giving the single data point. So that's what the cumulative or relative frequencies do. So the relative frequency gives you the percent that line up in that row, right? If you look at the top of page 311, we've got, the grade A, 4 people made an A. Well, it's 4 out of 25. Remember, it was 25 students. So that means it's 16%. So 16% of our students in this class made an A. And then it starts this frequency. And what they're going to do is they're just going to add it up along the way. So if we go down to B, 7 students made a B, right? Well, 7 out of 25, that's 28%. And then the cumulative frequency now, we add the number before, so 7 plus 4, 11. So what that tells me is I know 11 students have made at least a B, right? They've made a B or an A. They've made at least a B. So if we want to add the percents together, that's something like 44%? 44% have made at least a B, 16 plus 28%. And so on. So C, 9 made a C, which is the most common, right? 36%. But then when you add that up, that's 20. So that tells me 20 students out of 25, 20 students have made a C or better. That's actually pretty good for a math test, especially. Okay, very straightforward. I mean, it's just so the relative frequency gives you the percent for that column, for that row, I should say, and then the cumulative, it's adding it up on the side. Okay, it's just adding it up as you go. And then the book goes over something I believe we've talked about already. If we haven't, I will talk about it more. Maybe it was the other class. I think I'm teaching a business stat class at the same time. I think we've talked more about this in business stat. There's two types of data. Okay. Now you might try to find some gray areas, but if you find some gray areas in that, typically how they are used will be defined on what type of data they are. But there are two types of data. There's quantitative data and there's qualitative data. Your book goes over both. Qualitative is defined as data that describes qualities or characteristics. And then quantitative data represents counts or measures. So qualitative would be something like what color car you have, right? If I polled the class right now and said, what color car do you have? What you tell me is going to be qualitative data. It's qualitative because it's a quality of the car, right? It describes the type of car. Or what is your favorite, what's your favorite starburst, right? Real quick poll of the 3 students that are in this class. If you have a favorite starburst that you won't share with your sibling, what is your favorite starburst? Put it in here just because I'm curious and I'd like to know. But that would be qualitative data because it's a quality, right? It's the type of starburst. Quantitative, though, is pink. Definitely, that's mine. Qualitative or quantitative data, though, is different. It's it represents a number. So if I asked you, Red, Weston, you okay, buddy? No, I'm joking. Quantitative, though, is a little bit different. Quantitative, though, tells you a number. So if I asked age would be quantitative, height, things like that, GPA, things that represent a number or counts or measurements, those are all going to be quantitative data. Like if you, I'll give a good example of where this occurs at the same time in the real world. My wife is addicted to House Hunters. And I don't know if you've watched House Hunters. I am really sick of watching House Hunters. I don't think any of you know my wife, don't tell her that. But I am just sick of watching this damn show. It's about these couples. They have jobs where I don't know how they can afford the house they can afford. And then I have to care about the housing market in Boise, Idaho for 30 minutes. And it bothers me. And then I get sucked into it. And then I wonder why I'm sucked into watching this show about a couple who it's probably all fake anyway, because it's TV. But anyway, we can kind of use this. That's a good example, actually, of quantitative and qualitative data. So when these couples go look at these 3 houses, that's the whole premise of the show. They look at 3 houses, and then they choose a house at the end. And we can't leave the house until my wife finds out which house that these 2 strangers have picked to live in. Okay, anyway. But they look at these 3 houses, and you find out what they like. So a lot of times it'll be things like, oh, I want white counters, or not white counters, white cabinets. Or I want dark cabinets. Well, that's qualitative, right? It's a description. And so they'll look at those 3 houses, and maybe 2 of them will have qualitative, or will have qualitative. 2 of them will have white cabinets, and the third will have, black cabinets. And they'll have to, will they have to compromise on the third? Will the husband or wife have to compromise on the one with dark cabinets? But it has, let's say the square footage is bigger. Well, square footage is quantitative data, right? Or the price is lower, quantitative data. But then what if they like the neighborhood? Well, do you like the neighborhood? Yes or no? I mean, that's qualitative. So it's a descriptor, right? Now, if you can put numbers on it, like, well, the housing market's high, the average house is valued higher in this neighborhood. Well, that's quantitative. And it's kind of N, because N is in quantitative and it means number, right? Qual is quality, so quality of the data. I mean, that's just a basic example that I've thought up off the top of my head, because I swear I'm stuck in watching. I don't know. My wife goes from show to show. Currently, it is House Hunters. But anyway, those are good examples of the difference between qualitative and quantitative data. Then it talks about binning data. When we deal with quantitative data categories, it's often useful to group or bin. I've never heard it called bin, by the way. This is the only book I've ever used the terminology. The data into categories that cover a range of possible values. For example, in a table of income levels, it's going to be useful to group them together, right? If I wanted to look at all the income levels for maybe people with bachelor's degrees that live in Mountain Home, well, it's going to be crazy to look at all that data, right? To just look at every single income of every single person that has a bachelor's degree in Mountain Home. What'll be easier is to categorize it. Like, okay, well, we categorize it from 0 to 20,000 to 20,001 to 40,000, just groups of 20,000, right? And then put people in it. And that way we kind of have an idea. Or if you want to get closer, if you want to get more exact, you can make the group smaller, maybe down to the 10,000, width or a 5,000 width group. But your book does something like that. And it is nice. It's nice to represent those that quantitative data in categories because then we can graph it easier. We'll do that next in a minute. And then also it's just easier to visualize, right? It's a lot easier to visualize in a group like, oh, there's 25% of people that live in Mountain Home that have a bachelor's make between $40,000 and $50,000, right? So it's just kind of easier to interpret. Okay, so the next part on page 313 talks about bar graphs and pie charts. And it goes over what's important whenever you label graphs. There's 4 things that are important. The title and the caption, right? The graph should have a title or caption, or both, that explain what is being shown. If applicable, list the source of the data. So if you're going to use a bar chart or a pie chart for your paper, which I think I saw 1 or 2 in there, you need to have what the data actually represents, and then the source of the data. So, use that reference correctly for APA formatting. If you go on to Al Purdue's website, it's OWL Purdue, their website, they have a really good tutorials on how to put that into an APA style paper. But I need to know the reference, where this data came from, and then what's the actual data? What am I looking at, right? Second is the vertical scale and title. It says numbers along the vertical axis should clearly indicate the scale. The numbers should line up with the tick marks. The marks along the axes that precisely locate the numerical values. Include a label that describes the variable shown on the vertical axis. So we just need labels. We need labels and we need them used correctly, right? I'm going to do like a bar graph. I guess this way for you guys. This way. If we're going to do a bar graph, then the vertical axis has to show me tick marks. It can't just be random bars sitting out there in space. It's got to have tick marks to let me know the values. And then it also has to have the legend to let me know, actually, I guess say legend, but it's the vertical axis has to be labeled to let me know what the units are and what the variable is, right? So if we were counting humans on their grades, the vertical axis would be number of students, right? Number of students. So, if we look back at the teacher's example before, the A column for the bar graph would have 4, right? So there'd be 4 students, and that would correspond to 4 on the vertical line. And the horizontal scale and title, so the categories should be clearly indicated along the horizontal axis. Tick marks are not necessarily for qualitative data, but should be used with quantitative. Include a label that describes the variable that the categories represent. If you look on the second page on 314, they put the teacher's grades into a bar graph. Okay, so, and look, notice along the horizontal line, it gives for this example, it's going to give the grade, what each column is. So the A grade, there were 4 students. B, there were 7. Excuse me. So if it's quantitative data, which I have to flip over, well, like on 317, it's got scores written in a quantitative way. You would have to have numbers along that x-axis, that horizontal axis, to show where the group is. Excuse me. And legend. If multiple data sets are displayed on a single graph, include a legend or key to identify the individual sets. The main thing is really to understand, if you were going to look at this data, could you interpret it, right? I mean, you got to kind of put yourself in someone else's shoes and say, could I interpret this data? If you were going to make a bar graph or a pie chart or whatnot, if I looked at this, would I understand, oh, that means 25% of the students made that grade? Or can I tell which grade it is? Can I tell really how many students made that grade, right? And which group they line up with? Now, look, again, on this test, I am not going to make you find, or I'm not going to make you make a pie chart or a bar graph or histogram, things like that, but you're going to have to interpret it. So the next part is about the pie chart, and it's really about how to make each individual slice, and we're going to go over that for just a second. So if you look on the bottom of page 313, I'm going to kind of read along. It says pie charts are used primarily for relative frequencies because the total pie must always represent the total relative frequency of 100%. Excuse me, yeah, I don't know what the title was. Figure 5.4 on the next page shows a pie chart for the essay grade data. The size of each wedge is proportional to the relative frequency of the category it represents. In other words, each wedge spans an angle given by the formula. Wedge angle equals relative frequency times 360 degrees. So let's look at that for a minute. I'm going to do some basic data here off of our graph. Let me just hold on. One second, guys. I haven't used my desktop camera in a minute. Okay, here we go. So let's look at this real informal poll I just took about starbursts. Now there's 4 of us, and we only chose pink or red. Okay, so it was pink, red, and then I'm going to choose pink. Okay, so favorite starburst colors, 3 pinks and 1 red, right? Well, if we made a very basic frequency table for this one, it's just going to be pink. And then the number of pink is 3. Red, the number of red is 1. The frequency, though, so now there's 4 total, right? So therefore, I'm sorry, the relative frequency. So this would be frequency. And then the relative frequency is just the percent, which is kind of easy for this one because we only have 2. So 3 out of the 4 chose pink. So that's 75%, right? And then 25% chose red. And then cumulative frequency, well, pretty straightforward because this is a shorter graph. Cumulative frequency, it's going to be 3 and then 4, right? Because that's our total. Now, if we were going to make a pie chart out of this, we would use this relative frequency for our degrees of the pie chart. So let's look. If I wanted to find pink's wedge in the pie chart, well, it's going to equal 75%, so 0.75 times 360. So 0.75 times 360, 0.75 times 360. That's going to be 270. Now this is degrees, so it's going to be 270 degrees. So for the pie chart, not the best, I tried. We know that pink is going to take up 75% of this graph, which is 270 degrees. So I'm going to start right here and at the center, and I'm going to go around. Now look, we got 90 degrees here, 180 degrees here, and then 270 here. So this winds up being, I don't think I have pink. I do right now. I have red. Oh yeah, I do. Okay. So this would be pink's wedge on our pie chart. Now, we know the only thing left over is red, but I'm going to still find it by hand. So red's going to be 0.25 times 360 degrees. So 0.25 times 360, just popping that in my calculator. And I wind up with 90 degrees. Well, look, it is exactly what's left over. This is 90 degrees. So this is going to be red. So our little informal polling about which starburst color do you like is given here. So I might, on this test, I might ask how many degrees will be devoted to the red starburst, okay? And you're going to have to use the little formula to do that. Okay, wait, actually, this would be pink. How many degrees will be devoted to the pink starburst? Well, I know it's 75% of the data times 360 degrees. So that gives me 270. So 270 degrees will be devoted to the pink starburst. Okay. So look, again, I'm not making you make the graph because it's going to be a multiple choice or just a fill in the blank kind of answer. But I am going to make you answer some questions about the graph. Okay. And then then your book goes over some good examples. So you might want to look at some good examples in there. But then we're going to go over histograms and line charts. So a histogram actually is very similar to a bar graph. Let me show me. So a histogram is very similar to a bar graph, except that you use quantitative data with a histogram, and the bars touch each other. So it's still about grouping, it's still about categories, but instead of each column being separate, like with grades, each column is going to go together because they're going to be really numerically connected. And your book does a good example on page 317 when it comes to exam scores, but I wanted to kind of just show you, I'm going to make up an example. I'll kind of show you what I'm talking about here. So if we switch over to the document camera, let's say I looked at my grades on the last test. So QR test grades, and these are actual grades, not letter grades. Okay. So I looked at the last test in QR and I looked at the grades, and I'm going to list them top to bottom just because it'll make it easier for the next part. Hold on. Let's see here. Boom. Focus is kind of bad. So let's say I had someone make a 95, a 91, an 86, an 85, an 83. Then let's say a 79, 75, 72, 63, and then a 54. Why not? Okay, something like that. Well, to display this in a bar graph, or I'm sorry, in a histogram, I can make groups. So I can do groups of 10, maybe groups of 5, however I want to do. I'm going to do groups of 10 actually. So if I looked at groups of 10, and I want to make these into categories now. So if I want to make some categorical data. It starts at 50. Actually, let's start at the top. So I'm going to go 91 to 100. And then I'm going to do, actually, we'll do 90. It makes more sense, even though, so this will be a group of 11. But then we'll do 80 to 89. And then we'll do, 70 to 79. And then we'll need 60 to 69. And then lastly, we'll need 50 to 59, right? And then if I wanted to look at the number in each one of these, number of students, each one of these, 90, 91, I've got 2 students, right? And then I've got 3 in the next 2 groups, and then I've got 1 and 1. So the difference, now notice, remember in the bar graph, these were labeled A, B, C, D, and F, right? But in this one, we actually have, a group of numbers. So therefore, this would be quantitative data because it's the actual grades on the test. It's not qualitative data. So because of that, these bars would need to touch. It's not like, I know this sounds kind of goofy, but even though these are different groups, they're not disconnected different groups. They're in a linear fashion, right? It's not like, for instance, another extreme would be, if I asked you the number of car you drove, right? And you'd say white. Well, maybe there'd be 2 people that have white cars, 3 that had red, 3 that had black. Well, those groups would be totally disconnected. There would be no, there would be no need to butt each bar up in those groups, where with these groups, they connect to each other. So that means when we create this histogram, we need the bars to touch. So let's do low to high. So we're going to start at 50. We'll do 60, 70, 80, 90. Right, room there. And then we only go up to 3 students, so we're going to be a little lazy here and just do 1, 2, 3. Well, 50 to 60, I've only got 1 student in there, right? 60 to 70, I've only got 1 student. But notice the bars touch. And that's the difference between a histogram and a bar graph. So 70 to 80, I've got 3. Shoot up. And then I've got another 3. It wouldn't look good if I went down to 1 in that section. And then we go to 2. And we're done. Okay, so that's a very, very basic histogram. But now, again, the goal for this class and this test will be for you to interpret this. So it's very basic interpretation, right? Well, I've got 3 students, so I need to label these, right? Students, and then grades. I've got 3 students who scored between a 70 and an 80 on this last test, okay? That would be what I'm looking for the test and really for this class, what I want you to know. Your book goes over, actually kind of backtracking a little, on the bottom of page 317, the author goes over 3 different types of ways to visualize quantitative data. The first one is the histogram. It says a histogram is a bar graph for quantitative data categories. The bars have a natural order and the widths have a specific meaning, right? That's what we went over. The next is a line chart, and it just shows the data for each category as a dot, and the dots are connected with lines. Okay, if I wanted to be, I'm going to be a little lazy here. So for this example, if I wanted to make a dot chart out of it, let's use a different color. Well, this red line would be our line diagram. So we would just use a dot instead of the graphs. So a line graph or a line chart would go from the first data point to the next, and then you just connect the dots. Okay, where that red line is actually where the line chart is. I'm not a big fan of line charts because it looks as though they connect in a way, but these are groups. So it's not the worst way to display data. For this example, it's not the best way. And then last, we've got a time series graph, which is just a line or histogram in which the horizontal axis represents time. So if you see, that's a very specific example in the book. Okay, I'll leave it on here for now. So for homework in this section, for 5C, I'm going to make sure to choose the correct homework because of that one single time I didn't. And I caught myself. Now I have to do this every time. So for 5C, we're going to do 1 through 51 odd. And now I want you to really focus on interpretation. Okay? Actually, yeah, 1 through 51 odd. And focus on interpretation. So it starts on page 321. And I just want you to focus on interpretation because that's how I'm going to have to really kind of test you in this section because you won't be able to make a pie chart or make a bar graph. You'll have to actually interpret and find the wedge, find the percent or the degrees for the wedge of the pie chart. Really, that's the most math you might have to do in this section. Okay, so now turning on, let's go to 5D. Now look, guys, section 5D is really more about you reading it and asking questions. It's over graphics in the media, which we've talked a little bit about already. 5B was about, actually 5B, what was the title? Because something about, is this study valid, right? Yeah, should you believe a statistical study? Well, 5D kind of goes with that, but in the visual way. It talks about interpreting the graphics beyond, the basics. And the book goes over kind of, just some extra kind of graphs. I just want you to read it. If you have questions, let me know. They're very straightforward, right? If we've got multiple bar graphs or multiple line charts, the stack plot, which I feel like I've seen a lot of lately in the media. It's on the bottom of page 327. And then graphs of data. You can read that. I'm not worried about it. What I want to talk about, actually, hold on. I've never gotten a phone call in the middle of a class. That is crazy. I want to talk about the perception, actually the distortion, which is on page 332. I'm going to focus on that a little more. I'm going to let you read the previous section or the previous stuff because it's really just about reading it and knowing the examples. I'm not worried about that. You can do that. You can read. But I'm going to talk about this perceptual distortion because it happens all the time, okay? Especially in the media, especially around election season, but it happens all the time with data. And actually, I wonder if I can, I'm going to move my book over here so I don't have to talk about it. I can kind of show you guys. I'm going to move over. Okay. I'm just going to use the books example. This is probably some weird copyright infringement. Actually, it's not because it's for educational purposes. But the first type of perceptual distortion, or the caution, I should say, is perceptual distortion. And look, they make it as if these are relative, but they're not. Like if this was $1 and this is 63 cents and 39 cents, it is so hard to interpret really two-dimensionally when graphs do this. I mean, they do it all the time, and it makes it very hard to really understand what's going on. It says the links of the dollar are proportional to their spinning power, but our eyes are drawn to the areas which decline more than the links, right? So this length of the dollar really does correlate to the percent. So this length would be 39% of the $1, but our brains see area first. So this looks a lot smaller than 39%. To me, it looks like it's about a quarter, if not less, maybe 10% of this entire dollar. So that's a very common, and I don't know if you could say call it tactic, but it's definitely a common distortion used when you're looking at graphs in the media. And if you guys see something like this, take a picture of it, screenshot it, send it to me. I love seeing examples of these in the media. The next, which is extremely common, is messing with the scales on the left. This vertical scale, this happens all the time. So this graph is titled "Women as a Percent of All College Students," and it starts in 1910. It's at 40, and then it goes up, and then it comes back down. But if you look on the left, it looks like there's these huge, drastic changes compared to the right-hand graph, right? It looks like actually from here to here, it almost goes from, I don't know, it decreases by almost like 80%, right, from here to there. But in actuality, it went from about 47% to like 32%, right? Which is a big jump. I mean, that's a huge drop if you think of the percent of a certain type of demographic at a university over or less than 2 decades, right? That's a huge drop. But this just a visual way to kind of draw you in if you're not looking at the left-hand side, because when you scale out, you'll see that it's a trend that is just kind of going along, and it goes down and then it goes up, and really there have been more women in higher ed since that time, since the 70s. I thought it was before that, but yeah, there's just been a higher amount of females in higher education. But you can see how this could be distorted greatly. And all they did was change the scale on the left, right? They just used the really the y-axis for where the data occurs, okay? Where the data occurs. And then, they can distort it in a different way, which is actually manipulating the y-axis. Now, you can really make an argument that this is not manipulation, okay? Because the data on the left is not lying. It's telling you exactly what's going on. It's just your brain visually sees it a certain way. I'm going to tell you this is lying. To me, this was more lying, this computer speed example. But because instead of each digit meaning a single unit, it actually jumps from that. So each unit is actually given as base tens. So 10 to the 1, 10 to the 4th, 10 to the 7th, and 10 to the 10th. That is not a linear increase. It's not like 1, 2, 3, 4, 5. It is an exponential increase for each digit. So therefore, it makes it look as though computer speed from 1950 has been this linear pattern, where it has not. Of course, computer speed has grown exponentially in the last few decades. Okay, actually, it was growing exponentially all along. It just shot up the last 2 decades. Okay. I don't see this as much in the real world, But I will see it more in academic text, and you have to just be very careful that that y-axis is linear and not exponential, or sometimes logarithmic, which is okay if you don't know what those mean. I'm not worried about it, but just the main idea is when you're looking at the graph to be careful about the scaling on the left, okay? Be careful. This is way more common, okay? And then, yeah, the percent changes graph, which is always interesting to see, the change in college costs. So this isn't the actual change in the cost, it's the changes in the college cost. So if it's the percent change from year to year. So again, it's not wrong to put this down if your goal is to kind of see, hey, does the cost of college match inflation? Which inflation is typically around 3% each year. And if the cost of college matched inflation, you would have this nice flat line here, right? Even though it is increasing each year, you'd have a nice flat line. But this graph is looking at the change from year to year. And notice, I mean, it's beat inflation, actually, except at private universities in 2012. It's beat inflation for this entire gap, okay? Shooting up around 2004 at the public sector, okay, the public 4-year. But if you look at the actual data, of course, it's increasing all along because these are the percent increases from year to year. And then lastly, your book goes over pictographs and just says, be careful if it has additional artwork going on that you're just looking at the data. That's not a big deal. But that is all of this section. So really a lot like 5B, this section isn't about math. This section really is about visualization and interpretation. So I'm going to go back to me. So because it's not really about math, it's more about definitions. You just need to read it, look over it, and see if you have any additional questions based on it. And remember the test, though, is going to go over your interpretation, or I'm going to ask you to interpret the graph. And, what's wrong with these two graphs? Oh, the scaling is completely messed up, right? Something of that nature. The y-axis makes it look like there's these huge drops or gains in a certain demographic coming to college. But in actuality, they've just scaled the y-axis much greater, okay? All right, for homework in that section, actually, it didn't look like I gave you homework on the schedule. So for homework, I want you to start on page 336, and it's not that long. It's only 1 through 1 through 33 odd. So 1 through 33 odd, and it's really just about interpretation, visual interpretation of graphs, okay? Which will be on the test. Not real mathy, not real algebraic by any means, but definitely important in the real world. Okay, you three that are in the class, do you have any questions? You can raise your hand. You can write it in chat. Comments, concerns. Okay, I'm going to wait a little bit. Oh yeah. I'll get back with you, Annie. Quit being a difficult student. Oh guys, somebody watching this later. Miss Noblin is in the class right now, peer evaluating me. I am not talking down to a student. I am talking to her. Let me